So all trade-offs ultimately exist because resources are finite. Because of the finite resources, because of the limited resources, there exist trade-offs. Because time is also a resource, cost is also a resource, money is also a resource, and computing power is also a resource. So, and all these resources are limited. Time is limited. The budget, the money is also limited. Everything is resource finite. So, because of the finite resources, trade-offs exist. Now, if we look into some resources, so CPU, CPU is like the computational power. So computation is not free. So there is a constraint associated with CPU. So CPU constraints, if we talk about, we have limited instructions per second. Because there is a limitation on the number of instructions we can execute per second. Context switching overhead, because context switching, it takes some time. There is a lag associated with it, and it's a constraint. Contention between processes. Now, let us suppose you have a dual core architecture wherein two processors are working simultaneously. Still, there is a processors are competing to get processed, to get the CPU, to get the processor. So there is always a contention between the processors. So hence, CPU constraints are always there. Limited instructions per second, context switching overhead, contention between processors. Now, if we talk about the trade-offs involving CPU, so CPU load. Okay, so see, if we talk about the trade-off, so the first trade-off we can discuss is the disk space. Like if we try to optimize the disk space, then what we have to do, we have to compress the data. So compression, it will definitely save the disk space, but it will cost CPU because we will be needing to run some additional compression algorithms. That compression algorithms, it will definitely reduce the disk space utilization, but it will also incur some additional cost. If we try to optimize the security, so security we can consider encryption. Encryption will definitely improve security, but it adds latency. And if we try to optimize application logic, and for optimizing application logic, we can consider complex queries. But complex queries, it will definitely reduce the application logic, but increases the CPU load. So ultimately, if we try to optimize either the disk space, security, or application logic, ultimately we are increasing the CPU load. And because of that, there will be a latency and CPU will be occupied. So performance will get affected. So that's the trade-off. If we try to optimize one thing, we have to sacrifice the other dimension. So that's the trade-off. Now, one very interesting thing about CPU is that it is elastic in nature. Elastic in nature that we can scale it. Either we can do horizontal scaling or we can do vertical scaling. Where in horizontal scaling we can keep on adding more replicas of CPUs, and in vertical scaling we can improve or increase the computing power of the existing CPU by adding more processors into it. If it is dual core, we can make it quad core or octa core, wherein 8 processors are running simultaneously. Or we can do the horizontal scaling. So CPU is elastic, and that's a good thing. But still, it is elastic, that's totally fine, but still, it is never infinite. It is finite. It has to be finite. It cannot be infinite. And that's a limitation. And because of that, trade-off exists. If we talk about the second resource, that is memory. Now see here, when I talk about memory, I'm talking about the primary memory, that is the RAM. So if we talk about the characteristics of memory, so it is extremely fast. It is extremely fast. It is limited. This is a very big constraint. It is volatile in nature, wherein once the power is off, the data, it's gone. Data is not stored permanently in memory, and it is very expensive per byte, and hence it is limited because it is very expensive, and we cannot use like unlimited memory. It will cost money. Now, if we talk about the trade-offs associated with memory, now if we go for caching, what happens is that any repetitive data we want to access, instead of calling it from memory again and again, we can store it in an intermediary place called as cache, which is extremely fast as compared to memory. So with caching, definitely latency improvement we can get because our data, we want to access it frequently, we can just access it via cache. So caching, definitely it improves the latency, but risk is also associated, and there's a staleness risk. The data might become stale, and what it means is that, see, the source of truth is in the memory, the original record, and in the cache it's a replica of it. Now what if the original records get updated? Because processor is now taking that data from the cache and not the RAM, and if that data gets altered in the RAM, so processor will be making use of a old data. So stale means here old data, because the original data it got updated, but in the cache still the old data is there. So that risk is the staleness risk. So trade-off is there. Like if we over rely on caching, then staleness risk will amplify. If we go for in-memory database, so in-memory databases, it will definitely speed up. It will speed boost, but it will also at the same time increase cost, because we know that memory is expensive. Large memory footprints, it will reduce concurrency. So the idea is that if we try to optimize one dimension, we have to sacrifice the other dimension. So that's the trade-off we are talking about. And hence, all the decisions we will be taking as system engineering or system design, it has to be highly contextual, because the decision will depend on the problem which we are trying to solve or the goal we are trying to accomplish. There is no one hard and fast rule which we can apply in all the scenarios. For every scenario, the decision will be different because of the trade-off. Now let us look at one very important insight. See, memory optimizes speed at the cost of durability and money. So definitely we make use of memory. Why we use memory? Because we know that hard disk, it has got a significant lag. Like if you are accessing the data frequently from the hard disk, it has a significant lag, so the performance will decrease, it will degrade. So for high performance, for low latency, we have to make use of memory. So memory definitely it reduces the lag, it optimizes the speed, the performance. But with memory, we have cost, we have to bear the cost, and also the durability. And why durability? Because memory is volatile. The data in the memory, we cannot rely on that. It will fade away once the power is gone. So memory optimizes speed at the cost of durability and money. So it is fast but fragile and pricey. Disk. So here when I talk about disk, I'm talking about the hard disk, which is like the permanent storage. Now disk, they are durable but slow. So if we talk about the properties of the disk, so the one of the very important property of the disk is it is persistent, wherein the data is stored permanently, even power loss, the data will still be there. It is cheap as compared to memory, low cost storage, and it is slow, like the very high latency. It's like a very big drawback of disk that it is very slow as compared to memory. High latency is associated. If we talk about the trade-offs associated with the disk, so see, writing to disk, definitely it improves durability because the data is stored permanently. If you write the data on the disk instead of memory, then durability will increase, but also latency will increase. because the read write operation, IO operation on disk is like it has got lag, latency is associated with it. So that is a trade-off. Now, if we talk about replication, so if we replicate, if we make multiple copies of the data, then definitely it will improve fault tolerance. It will improve fault tolerance, no doubt in that. But it will also increase the write cost, because now we have to write on different locations because we are maintaining a copy, a backup. So that's the trade-off. So if we want to improve the fault tolerance, then we have to bear some cost. It will increase the write cost. And if we go for indexes, so with indexing, definitely we will get speed reads, but it will also result in slow writes and it will consume more disk. So that's the trade-off. So if we try to improve one dimension, we have to sacrifice the other dimension. That's the trade-off associated with the disk. So if we talk about the disk trade-off pattern, so while using disk, you pay for durability with time. Like you are preferring durability over time, because using disk means persistent storage. But at the same time, you are also affording or incurring more time. It takes more time for the read and write operation. So here the trade-off is that we are going for durability safety by sacrificing the latency and the cost, time and cost. So that's the idea. Now, if we talk about network, so network is the silent bottleneck. Now, network is basically the communication network, like the systems, they are connected in a network and they can exchange the data. Now, in network, so latency dominates distributed system. So in distributed system, multiple nodes are connected with each other, and that transfer or the information exchange, it takes some time. So latency is like a very big problem in distributed systems. Also, in in networking, packets gets dropped. So it's a reality of a network. So latency, packet drop, message may arrive late, message may be duplicated, or message may be out of order. So these are like some very harsh realities of network. So network failures, it look like slow machines. So it's also a very harsh reality wherein we keep on waiting without realizing that some network failure is there, some fault is there in the network, and we feel that network is slow. That's why the message haven't like it hasn't arrived till yet. So we keep on waiting for the message to arrive without realizing the network failure. So network failures, it always look like slow machines. So these are like some very harsh realities of network which we have to deal, like latency, dropping of packets, messages arriving late, out of order, duplicated. So network failures, it look like slow machines. Now, what are the trade-offs if we talk about? So distributed systems, they scale better but fail harder. So uh, this is a very important discussion we are making. So in distributed systems, the scalability is the thing which we are trying to achieve, because in distributed systems we keep on adding more and more nodes and we are scaling it up. So distributed systems, we are trying to optimize the scale, we are trying to scale up the system, but the thing which we are sacrificing is the simplicity, because distributed system, it is becoming more and more complex, and hence handling uh, failure is very tough, because when the distributed system fails, it fails harder, and that is what we are sacrificing. So that's a trade-off. Now in a network, replication improves availability but hurts consistency. So when we maintain multiple replicas of the same node, definitely it improves availability. Like once the like one node is down, we can call the backup node. But also maintaining consistency is very tough, because any update you have to update it on all the replicas at the same time. So that's a challenge. Cross region systems improve resilience but increase latency. So latency we already saw that. So the idea is that if we try to like make a network covering different geographical regions, that's that will definitely improve the resilience, but also because of the scale of the network, uh, geography, different geographies, the latency will come into the picture. Latency will start dominating. So it's a trade-off. If we are trying to optimize one dimension, ultimately we are sacrificing and suffering the other dimension. So one very harsh reality about the network is the network is unreliable by design. So we cannot rely on the network, and hence we have to assume, or we have to like make a mind make up that okay, network will fail, and hence we have to work with the mindset how to handle that failure, because network is highly unreliable by design, and we have to keep in mind that network failure is common, and the most important question in front of us is how we will handle the failure.